Welcome to SCH 306, Inorganic Chemistry 3. I am Dr. Kwach, and that is my contact. Inorganic Chemistry 3 will basically be dealing with the D block elements of the periodic table. You remember we had earlier on looked at S and P block elements in SCH 205. Now in 306, we look at the chemistry of the D block elements. Basically, these are the elements contained in the periodic table between groups 3 and 12, where it is the D orbital that is being progressively filled. They comprise three main series of the transition metals, that is 3D series beginning from scandium to zinc, and 4D series from yttrium to cadmium, then 5D series from lanthanum to mercury, omitting cerium and lutetium. Then there's the fourth series, that's the 6D series. This begins with actinium, but is an incomplete series. Basically, a transition element may be defined as that element which has an incomplete D orbital either in its ground state or in any of its common oxidation states. Zinc, cadmium, and mercury, both of which are group 12, have a full configuration of D10 in their ground state and do not have any of their common oxidation states having incomplete D configuration, and therefore they are not regarded as transition metals. However, being the end metals of the three transition series, their chemistry will be studied alongside the transition metals. It's the presence of this partial filled D orbital that makes the chemistry of these elements interesting. One fundamental chemistry fact of the importance of valence electrons in the chemistry of elements still hold for these elements. And we note that the chemistry of these elements is important to us because some of those metals are like silver, gold, and platinum, which are very precious metals, belong to this group. Other industrially important metals like iron, copper, and titanium are also transition metals. D block occupies the middle section of the periodic table, that is between S and P blocks. These elements, as I've said earlier, have their penultimate orbital being filled by electrons. Penultimate orbitals here refer to the inner orbital D, because D is an n-1 orbital for these elements, where n is the principal quantum number, but you have the ns orbital, which is now the outer orbital or the ultimate orbital. So these are the elements, as you will see, from scandium to zinc is series 1, where 3D orbital is being filled. The 4s, as you are seeing, this is the ultimate or the outer, but the 3D is the immediate inner orbital, and it's the one being filled with electrons progressively from scandium to zinc in series 1, and from yttrium to cadmium in series 2, then from lanthanum to mercury in series 3. If you consider the electronic configurations of these elements, we can have a general configuration where you have the penultimate D orbital being progressively filled from 1 to 10, where you have n-1 means it is the penultimate. Then there's the outer ns orbital, which can have 1 or 2 depending on the element and stability, energy stability issues considered. For instance, we'll be considering half-filled and full-filled stabilities to determine whether the NS would have 1 electron or 2 electrons. For instance, consider an element like chromium which will have a configuration of 3d5-4s1 instead of 3d4-4s2, because it's the s orbital that is supposed to be filled first before this d orbital is filled. So you will find that instead of 4s having 2 electrons, one of the electrons is transferred to 3d, so that you have a 3d5. The d5 is half filled stability, so the electrons will move from S to D. And this is possible because the energy gap between the 3D and the 4s orbitals is very small. The electrons can easily move with a slight change in energy. A similar case is also seen with copper, where the configuration is 3d10-4s1 instead of the expected 3d9-4s2. The electronic configuration of zinc, cadmium, and mercury may be represented by a general formula of the penultimate orbital having d10 and ns2. Okay. The orbitals in these elements are completely filled in the ground state, and therefore, even if you have the ground state at d10, if you form their common cations by removing the ns orbital, still the d will be completely filled. So they are not transition elements. The d orbitals usually are peripheral. They project towards the outer of the atom as opposed to the s and p, and therefore they are more influenced by the surroundings, as well as they affect atoms or molecules that surround them. So the surrounding would affect them, they would also affect the surrounding atoms or molecules. In some respects, ions of a given dn configuration, that is n1 to 9, may have similar magnetic and electronic properties. With the partly filled d orbitals, the elements exhibit certain characteristic properties that make their chemistry so very interesting, and this include display of variety of oxidation states, formation of colored ions, and formation of complexes with ligands, where ligands are electron donor species. Transition metals and their compounds also exhibit catalytic properties and paramagnetic behavior. And all catalytic property usually is exhibited by these elements because of the existence of a variety of oxidation states. So they can be in one state, in one oxidation state as a catalyst, or a point where now they transit to the products, and then when they accede to the products, they can display a different oxidation state. There's also paramagnetic behavior that usually is exhibited by this, and mainly because of the electrons which are not paired, that are found in the d orbitals. But most of these properties we look at later on. So if we look at some general properties, we think of the lattice structure. Basically, these are metals. Sometimes they are called transition metals because they display those metallic properties like high tensile strength, ductility, malleability, high thermal and electric conductivity, and metallic lustre. With the exception of zinc, cadmium, mercury, and manganese, they have all the typical metallic structures at normal temperatures. So this displays the metallic structures can be HCP, can be body-centered, cubic, and so on, just like I've seen in other crystalline structures. On the melting points, the transition metals are very hard and have low volatility. The melting and boiling point are generally high, and this is attributed to the fact that they have a number of electrons that take place in the metallic bonding, and these electrons are both the ns and the n-1d electrons, because those two orbitals are very close and there are a number of electrons that occupy them. In a row, the melting points would rise to a maximum at around D5, and after that, regularly they reduce as atomic number increase. So there are some exceptions, as you would see in manganese and in technetium. So that is what is shown here. These are the three series. So you see a rise up to around 5, then a drop. But technetium and manganese are exceptions. Then enthalpies of atomization. This is the energy you would need to take these atoms to the gaseous form. These have a maxima at the middle of each series, indicating that the unpaired electrons per d orbital is favorable for strong interatomic interaction. And generally, the more the valence electrons, the stronger is the resultant bonding. So this is also a graph of enthalpy of atomization as it increases and then reduce with increase in atomic numbers. You can also see from that graph that metals of the second and third series have greater enthalpies of atomization than corresponding elements of the first series. And this accounts for the occurrence of much more frequent metal-metal bonding in compounds of heavy transition metals. Atomic sizes of transition metals, atomic and ionic sizes, this would follow the normal trend. Generally, you expect a general decrease with increase in effective nuclear charge. And since the shielding of the d electron is weak, it means the effective nuclear charge would be much more as you go across, leading to decrease in radii. This trend is observed in the atomic area of given series. However, the variation within the series is quite small. When you check now, like in this, you'll see that general decrease, but as you go, then the decrease becomes smaller. What is noteworthy is that between the second and the third series, you would see that there is a large difference in the sizes, and this is because at the third series now, you begin to fill the 4f orbital with electrons. These are 14 electrons that are added, and f orbitals are the weakest in shielding, meaning there is a lot of the charge that will be reaching the left charge. You have the atoms shrinking more. So that is what is this is what has been explained there, and you see that that shrinking, over shrinking of the orbit of the atoms due to the filling of 4f orbital is what is referred to here as the lanthanoid contraction. Okay, that has been explained. So these are some of those physical properties that I've explained there. You will refer to them later. On ionization enthalpies, you realize due to an increase in nuclear charge, the enthalpies of ionization is supposed to be increasing across every series. Although the first ionization enthalpy is generally increases, but the magnitude of this increase in the second and third ionization enthalpies for the successive elements is much higher. Okay, you would get some irregular trends in the first ionization enthalpy of 3D metals, and this is of no much chemical significance. However, considering that the removal of an electron alters the relative energies of 4s and 3d orbitals, that would account for that. If you consider the unipositive ions here, configurations of 4s electrons, then there will be a reorganization of the ionization with some gain in exchange energy, so that some electrons, as we have said, in chromium and in zinc would move from 4s to 3 or 4d orbitals. The dominant term in the second ionization enthalpy, which shows usually high values for chromium and copper, is where D5 and D10 configuration of the M+ ions are disrupted. So if you disrupt that, it means you are disrupting stability, so you need a lot of energy to do that. Zinc has a correspondingly low ionization because the removal of an electron would allow for production of a D10 configuration, which is very stable. The trend in the third ionization enthalpies is not complicated by the 4s orbital factor, and the greater difficulty of removing an electron from the D5 ions when is imposed upon the general increased trend would explain. Okay, then finally we think of the oxidation states. These oxidation states, one thing we notice that these elements exhibit a variety of oxidation states that we have seen earlier, and you would see from scandium to zirconium the different oxidation states. The oxidation states that are in bold are the common oxidation states. As you would see, manganese has positive 7 and positive 2 as common, chromium positive 6 and 5. Of course, titanium should have positive 4, and the others as shown in the table. So that is explained at this point, and you would note that the lesser number of oxidation states at the extreme end stems from either too few electrons to lose or share, or too many d electrons, hence fewer orbitals available in which to share the electrons for higher valence. So this explains why, unlike the S and the P block elements, where the higher oxidation states would become more and more stable as you increase the atomic size, here you realize it goes up to around manganese, and then the higher oxidation states begin to reduce as you go to more higher atomic number elements. So this is what is explained here. So that variability in oxidation states is a characteristic of transition elements and is arising out of incomplete filling of d orbitals in such a way that the oxidation states differ from each other just by unity, unlike the p orbital elements, which differ by up to 2 electrons. Okay, so if you consider the P, this is what I've just explained. For low oxidation states, when a complex compound with ligands capable of Y-acceptor character in addition to the sigma bonding, like in nickel cobaltate and iron cobaltate. The oxidation state of nickel and iron in this is 0. So that is about the properties of these elements.